are Cardio นั้นก็จริงๆ team. Today we are going to talk about cardiac resynchronization therapy defibrillator or CRTD. So let's begin with this video. The cardiac resynchronization therapy defibrillator or CRTD is the alternative treatment for the heart failure patients with a high risk for sudden cardiac death. CRTD is the combination of an implantable cardioverter defibrillator and a pacemaker to treat the patients with slow, fast, and very fast heartbeats by the electric pulse. Moreover, it can help the heart to work more synchronized in the left ventricle and right ventricle. The device consists of two parts, which are the body of pacemaker and the leads.
Implantation. The device body is implanted under the muscle layer in the area under the collarbone. The three leads are implanted through a subclavian vein, then separated to that specific implant site. Our device appearance is designed from physical curve design, which has the four-part curve and smooth edge of the device in the connector header and bottom. It can reduce 30% of skin pressure and enhance the patient to be more comfortable. The connector block also labels the channel of lead insertion by color to avoid the mistake of lead insertion. The design of right atrial lead is based on a patient lead with IS1 bipolar connector. The cathode of this lead is located in the tip electrode and another electrode acts as anode. The fixation helix is located at the tip electrode for fixing lead. For the suture sweep, it is used to immobilize and secure the lead in a desired site. For lead accessory, the first one is silicone terminal lead cap that is used to secure the lead terminal. Another accessory is a C-curve stylet that is used to guide the lead. The design of right ventricular lead is based on a pacing and defibrillation lead with the F4LLHO bipolar connector in a single coil model. The coil electrode acts as anode and the tip electrode acts as cathode to perform sensing and defibrillating shock. The fixation helix is located at the tip electrode. For lead accessory, the first one is lead cap design based on the EZ4 connector tool used to secure lead terminal, act as a medium during evaluation of lead performance, tunes the helix, and guides stylet into the lead. The second one is J-curve stylet, is used to guide the lead. The design of left ventricular lead is based on pacing quadripolar lead with IS4LLL connector. The four electrodes act as cathode and anode, except the distal electrode only acts as cathode. This lead has three tip configuration consisting of long tip spiral configuration, straight tip configuration, and short tip spiral configuration. The marker bands are only in spiral configuration. For lead accessory, lead cap design based on a QTX4 connector tool to secure lead terminals during implantation and act as a medium during lead performance evaluation.
For the materials, we divide into two main parts. First, the body of device. The upper connector block is made of polyurethane. The case is made of titanium. And the battery is lithium iodine battery. The second part is leads. If you zoom in, the tip of electrode is made of silicone coating with dexamethasone sodium phosphate. The electrodes are made of platinum iridium coating with sterloid elution. The conductors are made of MP35N, which is a nickel cobalt based alloy, together with silver. The insulators are made of silicone polyurethane fluoropolymer, silicone polyurethane copolymer, and each material is for each layer. And the conductor pins are made of 316L stainless steel, so we use the active mechanism for our device.
Block diagram. A block diagram demonstrates the overview workflow and main components in the device. The color indicates group components and arrows.
Magnetic resonance imaging or MRI can cause negative effects on our internal component circuitry, especially the ferromagnetic part. Who is wondering about MRI detection and MRI mode? Let's take a few minutes on this. When the magnetic field is detected, each mode is selected by the condition of the patient, whether pacemaker dependent or independent. The first mode is asynchronous pacing for dependent pacemaker patients to pace at a specific rate and time. Another is temporarily deactivated mode, which is for the independent pacemaker patient. This mode is neither sense nor shock to prevent inappropriate pacing or shock.
For the mode that the Hall sensor doesn't detect the MRI, the electrodes in each chamber will sense the signal and send all of them through the leads. The signal goes through the sensing circuit to be filtered and amplified. All of the obtained data are stored in the memory of MCU. After that, there is the condition to separate the patient that they should be pacing or shocking. For pacing, the signal passed through the adaptive CRT algorithm that we will explain more in the next part. Then send it to the pulse generator to generate the electric pulse. And for shocking, the accelerometer will check if the fast heart rate occurs because of the exercise or not. If it is from the exercise, the device will not do anything. But if not, the signal goes to the defibrillator to generate the electric shock. Then the device sends the electric signal through the leads and stimulate each chamber of the heart with the electrodes. To explain more about the adaptive CRT algorithm, the CRTD will check whether the heart has a regular rhythm or not. If there is a regular rhythm, it will be evaluated the AV intrinsic, which is less than or equal to 200 milliseconds. When it has passed, if the heart rate is lower than or equal to 100 beats per minute, the adaptive LV pacing function will be worked. However, if only one of above conditions is not met, the adaptive BIV function is worked instead. For the adaptive LV pacing function, the left ventricle is the only chamber to be paced at about 70% of the AV interval. And for the adaptive BIV function, the left and right ventricle are prepared to be paced by optimizing the AV and VV delays. AV delay is adjusted to pace after 30 milliseconds of P wave, but before at least 50 milliseconds of QRS period. After that, check whether the suspend condition has existed in the last step or not. If yes, go back to check it again. If no, the non-adaptive function occurs.
The Hall effect sensor is used to detect the magnetic field around the device. If the magnetic field is present, the output voltage will be half of the supply voltage. To connect the Hall sensor to the microcontroller, the datasheet recommended adding a capacitor and resistor in between. The purpose of the sensing circuit is to sense the desired signal. Starting with a differential amplifier as an instrumentation amplifier to receive the difference of two input signals from electrodes as bipolar recording. The result is known as intracardiac electrogram or IEGM. The next part is filters that allow only the selected signal to pass following the criteria of the cutoff frequency. We have high pass, low pass, and notch filters separately. A non-inverting amplifier can amplify the signal without shift the signal to the opposite side, and buffer is applied next to the amplifier. Lastly, we have a diode, allowing the flow of positive direction, since the next process is analyzed by microcontroller.
Let's move to the next important part, which is MCU. You may know this word, right? MCU or microcontroller unit. It is a small computer on an integrated circuit chip. In this system, it acts as a core function which collaborates to the subsystems scene number 1 to number 8. Due to the previous talk, the MCU works with the Hall sensor for adjusting the mode when detecting the MRI. The MCU also receives the heart signals from the sensing circuit. Those signals will be analyzed by algorithm in MCU. For the pacing mode, the MCU mainly works with digital potentiometer and pulse generator. The MCU has a duty to send signal to both of them for starting their functions. For the shocking circuit number 5, the MCU sends the signal to control the metal oxide semiconductor field effect transistor, or MOSFET, inside the circuit. Okay, we are now more than halfway of this. In the parallel way, the accelerometer gives the MCU a signal for activity evaluation. This can prevent the unexpected treatment, such as pressing because of high heart rate during exercise. For number 7, the MCU and intrathoracic impedance circuit work in a loop. the MCU sends signal to the circuit and then gets the result back to calculate the beating cycle, which can predict level of patient's symptom. If he may get worse, the MCU will order the buzzer to warn by sound. And finally, the MCU is added memory via using level shifter. For the MCU module, we use QN9090T from NXP Semiconductors. There are a lot of features which are suitable for our system, such as low power consumption, more memory, analog to digital converter, and Bluetooth. Okay, then throw back to the box number 3. Can you imagine what does the digital potentiometer looks like? Yes, its function is similar to analog potentiometer, but using digital signal to control. The left side picture shows the function inside the digital potentiometer, which has a lot of resistor ladders. Each tab can create different resistance values. When it is closed, it acts like a gate to control the level of voltage. By the way, the various voltage the patient needs depends on his condition. Next, focus on the right section, which is power generator. To activate it, the MCU has to order the transistor at the beginning first, and 4 MOSFETs of this system create different voltage values between anode and cathode, due to the voltage after adjusting from digital potentiometer, and the result will be sent to the patient's heart for pacing mode.
Well, that is the end of the power generation. Do you think it's such a cliffhanger or feel uneasy because now you're just aware that sometimes it's not enough to stop the trick? Here is the solution where our protagonists play a role. Let's recall what that the letter D stands for. Yes, it stands for Defibrillator. If the pacing signal can correct the heart rate, then shock it with high power arms will reset the heart and allow the pacing part to take over again. First, DC from the battery will be inverted to the alternating current by switching MOSFET on and off. Then, increase the voltage up to 800 volts using the transformer and convert it back to DC before charging the high voltage capacitor. The electrode connected to the heart will let the current flow back and forth controlled by H-bit module, and the characteristic of the biphasic shocking power is controlled by the microcontroller. If that is not enough to unfold your feeling, then let me introduce you about the spin-off. It is a section of the physiology sensor. This will help our device to clarify either it is ventricular tachycardia or your heart just beating so fast due to your activity during that time, and also alarm you before your symptoms get worsening. First, it is the activity sensor. In this case, we decide to use the accelerometer. It allows our device to detect the movement from either 4 or 6 directions of the surroundings. This will help our device to don't misunderstanding your condition. Next is the intrathoracic impedance measuring. In this one, the rectangular alternating current with the constant voltage is delivered to the chosen electrode with the housing electrodes as a ground. Then, the voltage across the heart will be read by the ADC pin to calculate the resistance across the intrathoracic area. This value indicates the incidence of the edema, which is the signal of the worsening. Other than that, to help it predict more precisely, the shortness of breathing during resting can help, and this data can be acquired without using an extra circuit, so we can obtain it by analyzing from rise and fall of impedance. This is threshold for our alarm system. If there is at least 2 out of this size that last for 1 week, then the device will alarm you to meet the doctor beforehand.
Thank you, and this is our end credit.